Hello everyone, my name is Ming. Today I'm going to talk about harvesting and logistic growth in differential equation. So let's see our questions today. Model 1, logistic growth. Let's suppose y of t represents the number of fish at time t in the years in the pound. Then the fish population is growing logistically and governed by the differential equation below. The graph of dy over dt as a function of y is given in figure 1. This is figure 1, actually. Then, question 1. What is the carrying capacity? What would happen when we reach the capacity? Before answering this question, we can first explain the graph. On the x-axis, we can see the f represents the population or the number of fish in the pound. It is ranging from 0 to 200. On the y-axis, df over dt is actually representing the growth rate of the population. So when we're defining the carrying capacity, we're just looking at the biggest value on the x-axis, which is 200. The other reason I'm saying 200 as a carrying capacity is when the curve reaches this point, the dependent value reaches 0, which means the growth rate is 0. After this point, there will be no increase in this population. So I'll just say the carrying capacity is 200, and when the population reached the capacity, the population would not grow bigger. So it will either decrease or remain at 200. Decrease or remain. Let's move on to the next one. Find the general solution for the differential equation dy over dt equals y times parentheses 2 minus 0.01 y. First of all, only by looking at it, we can see this is a first order differential equation. So the next step we're going to do is to find if this is separable. So for me, I'll just move dt to the right side and move this whole thing to the left side. Then we will get dy over y times 2 minus 0.01 y equals dt. Further simplify it, I will get 2y minus 0.01 y squared is dt. To solve this, we have to take the integral on both sides. So we'll get integral of the left-hand side equals integral of the right-hand side. Then let's figure out the left-hand side first. This is a little bit complicated. Look at this, we will get integral of 1 over the whole thing dy. I'll first multiply 100 or negative 100 on the denominator and the numerator. Then I will get negative 100 over y squared minus 200 times of y dy. In the next step, I'll firstly put the negative 100 outside, then I'll factor the denominator. So I will get negative 100 times integral of 1 over, I'll put y squared out. So we will get y squared times of 1 minus 200 over y dy. We cannot see the solution from here, so I'll just take the substitution of this one. I'll let u equals 1 minus 200 over y. Then we know that the integral of negative 1 over y is 1 over y squared. So in this case, du is actually 200 over y squared dy. Then I put this thing to the right, the left, I will get dy equals y squared over 200 times of du. Then I substitute it back, I will get negative 100 times integral of 1 over y squared times 1 over u times y squared over 200 times of du. Then these two y squared canceled out, and I can put the 1 over 200 out. Then I will get negative 1/2 times integral of y over u du. This is quite clear to see what integral would be. We will get negative 1/2 times natural log of u. Then I'll substitute back the u. We will get negative 1/2 times natural log of absolute value of 1 over 200 over y. So this is the solution for the left-hand side. So now let's move on to the right-hand side. Put it right here. The right-hand side, we'll get the integral of dt from here. We can say integral of dt is actually integral of 1 times dt. We know the integral of t is 1, so in this case, we will get t plus c. So I put together left-hand side and right-hand side together. I will get negative 1/2 times natural log of absolute value of 1 minus 200 over y equals t plus c. I can actually simplify this, but I'll leave it here because it's clear enough to see the general solution. And this is also easier to use in the next step. I will copy and paste this into the next page. Copy, paste. Question 3, we're going to find the general solution, the solution satisfying the initial values. So in these 3 cases, I'm just plugging, you see, y of 0, and y of 0, which means t is 0 in all 3 cases. In the first case, y is equal to 50. In the second case, y is equal to 100, and the last one, y is equal to 200. So firstly, I'll plug in t equals 0 and y equals 50. I will get negative 1/2 times natural log of absolute value of 1 minus 200 over 50, which is 4, equals 0 plus c. In this case, I will get negative 1/2 times natural log of 3 is c. After calculating by the calculator, I'll find the c is actually negative 0.549. In the second case, I'll do the same process, plug in these two numbers. I will get negative 1/2 times natural log of 1 minus 200 over 100, which is 1, equals 0 plus c. I will get negative 1/2 times natural log of 0 is c. Oh, I'm sorry. It is 2. Natural log of 1 is c. We know natural log of c is 0. Natural log of 1 is 0, I'm sorry. So in this case, we will get c is equal to 0. In the last case, let's plug in t and y respectively. We will get negative 1/2 times natural log of 1 minus absolute value of y minus 200 over 200, which is 1, equals 0 plus c. We'll get negative 1/2 times natural log of 0 equals c. Natural log of 0 is actually undefined. It's right here, it's undefined. So c in this case does not exist. So let's move on to the second question. The next question. We are asked to plot the solutions. Firstly, we have to define the shape of the original curve, because what we already seen is df over dt, and x-axis is y is f. We see a curve like this. When we're defining the original graph, which is f and t, we know that the dependent value in the first graph is actually the slope of the second graph. So in this case, we can see in the first graph, the dependent value went up and down, which means the slope of this is shifting up and down. So I can simplify this concept into a shape like this, like the letter S. We see the slope of it is getting bigger and bigger, but when it reaches this point, it will get smaller and smaller, then to 0. Slope right here is 0. Firstly, we define the shape, and we use this shape to the next question. We would have to define the intercepts. The intercepts are what we just saw in the previous question. It is the initial values. We know y of 0 is 50 in the first case, y of 0 is 100 in the second case, and y of 0 is 200 in the third case, which means we have to shift this graph to satisfy these 3 initial values. We will see when the intercept is 50, we will get something like this. This is 50. When the intercept is 100, we will get something like this. It looks terrible, but I hope it makes sense. When the intercept is 200, I don't think we can get a specific graph, because after this point, we don't know any change. We just know the population will now grow bigger. So I'll just write something here. It's 200. Maybe the graph is around here. I'm not quite sure. Let's move on to this next one. So here's the conclusion. In short, the 3 graphs looks like this. In the 3 conditions, the populations of the pound reaches 200 at time T1, T2, and T3 respectively. We can tell from the initial values that T1 is T2 minus 0.549. It is from here, what we just defined. It's a little bit shorter. And we can also know T3 equals to 0 because the initial value, the initial population of the population is 200, which means the population of A condition reaches 200 is 0.549 T times slower than the population of B. Then the population of C will remain or decrease. I can also say the graph A is parallel to graph B, just like what I said. It's just like something, the original graph shifting up and down, left and right. They have the exact same shape, but different intercepts. We finished Model 1, so let's move on to Model 2. Model 2 is logistic growth and harvesting. Suppose that fish are harvested from the pound at a continuous rate of 8 fish per year, where H is a constant. Let P be the number of fish in the pound at time T in years with harvesting. The population is now governed by the differential equation below, right here. An explanation of why the population P satisfies this differential equation is that the rate of change dP over dt as a function of P and independent of the harvesting would be expression from Model 1. The term H represents an outflow term for the constant rate for harvesting fish. Let's move on to the first question. Draw the slope fields for h equals to 70, 100, and 120, respectively. Sketch the graph of p against t with initial values. We see these three conditions. I use some online resources to help me plot slope fields. Let's check it out. First of all, when h equals to 70, we will get function like here, y prime, no, not quite y prime, but dp over dt is 2y minus 0.01 times y squared minus 70. We'll get a slope field like this. The black line indicates p of 0 equals 42. The blue line indicates p of 0 is 101. And the purple line indicates p of 0 is 150. These three numbers are actually the y-intercepts. So look at here. I try to be precise. These three graphs would look like this. Then in the second condition, when h equals to 100, we will get a slope field like this. We see the number change. This is h. Slope field would like this. These three lines, black line 42, blue line 101, purple line 150. And the last one is when h equals to 120. This is a slope field I drew, and here are the three intercepts. I hope that makes sense. So in conclusion, according to the first graph, we saw when h equals to 70, here is a small draft of it. We can conclude that when there were 42 fish in a pound initially, which means p of 0 is 42, the population would decrease to 0, right here, to 0. When there were 101 fish in a pound initially, the population would grow to 150, right here. Then when there were 150 fish in a pound initially, the population would remain at 150. Let's see the next condition. When h equals to 100, which means when 100 fish are harvested at one time, we will see when there were 42 fish in a pound initially, the population would decrease to 0. Right here, it hits 0 after a period of time. Then secondly, when there were 101 fish in a pound initially, the population will remain at 100, like the straight line in the middle. Then lastly, when there were 150 in a pound initially, the population would decrease and remain at 100, like this line here. In the last condition, when h equals to 120, when 120 fish are harvested at one time, we will see the population will decrease no matter what initial values are. They all hit 0 after different periods of time. Let's move on to the next question. What levels of harvesting lead to a sustainable yield? Which means in long run, after harvesting, the population will not depleted. Let's first look at the slope field. I give an answer of h equals to 100, so let me explain why. Let's look at the second graph first. This is a slope field we just saw in the previous page. As long as there are more than 100 fish in a pound, we can see that the population will always remain at 100. It will not decrease to 0 or reach too high. So let's back to the first graph. Look at this one. When there are 100 fish are harvested, which means there will be 100 fish remain pound from here to here. Are 100 fish remain in the pound? We can see the growth rate hit this point. this is the highest dependent value, which means at this point, the population has the highest potential growth rate. So we don't have to worry about the pound being depleted or it reached so high. In short, in long run, when there are 100 fish in a pound, the population has the highest growth rate. Secondly, as long as there are more than 100 fish in a pound, no matter how many have been harvested, the population will not decrease to 0, but remain at 100. Back to the first one. Remain at 100 means the population has the highest growth rate. Third question, what would happen when H is close to 0, and what about H is close to 100? We can look at a graph here. When H is close to 0, which means there are no fish that are harvested. So the population will look like these two graphs. The population will grow to 200 and remain at 200, which is the carrying capacity. So this situation will not benefit in long run because we don't know what would happen after reaching the carrying capacity. If it maybe it will decrease to 0, maybe it will remain at 200 for for such a long time. We don't know that. So I'll just say when H is close to 0, this is not a proper idea. What would happen when H is close to 100? This small graph is what we saw in the previous pages from the slope field. We see this dot is actually 100. When the initial value of the population is larger than 100, the population would remain at 100 in long run. But if the number is smaller than 100, it would always drop to 0, which could lead to a depletion. Thank you for watching my video. I hope what I said makes sense. And I'll see you next time. Have a nice day.